The Kruskal-Wallis test is like a nonparametric ANOVA. And it's here in the same chapter as the squared ranks test, which is about variance because it involves very similar calculations as the variance test. But it's important to remember that the V in ANOVA is a misnomer because it's really a test about means. All right, so the data, just like with ANOVA, is going to be double indexed. So we're going to have I equals 1 up to nj, and j equals 1 up to m. So I have m groups of samples that may not be all the same number of observations. And what we want to check is if the means are the same for everybody, which I'm going to generically denote as mu, but it doesn't really matter what value that is, for all of our observations regardless of I and j, versus the alternative that there is a j and a k, so that is two different groups where the means are different. So for some j not equal to k, and that's for all I. So just like in ANOVA, the null is that they all have the same mean, and the alternative is that there's a pair of samples or a pair of groups where the means differ. And we want to test that hypothesis. So how do we do it? Let's let Rij denote the ranks of the combined sample. So that is combining samples from all of the groups. So of all n equals sum of nj observations. Okay. And then let's denote Rj bar. Let's let that be the aggregate of all of the ranks in the jth group after you've done the ranking on the combined sample. Okay, so we're getting the aggregates of the individual ranks in each group, and then combine these site adjusted, combine size adjusted squares of these ranks, of these rank aggregates. Okay, so what I mean by that is take each of these Rj bars, square them, divide by how many there are in that group, and then add that up. Okay, so this is our test statistic. Okay, let me show you what I mean by that with an example. So this example pools together all of the metro data that we had from previous chapters. Some of these I did not do in actual video vignettes, but they do occur in other examples in the book. So this is the fare card data. I should write that here. So this is combined fare card data from previous chapters. And we want to see if they all have the same mean or not. Okay, so there's the data pasted in. Don't forget your automations for ANOVA from chapter 6. What I mean by that is, if we want to get all these nj's, we can just s-apply the full list to the length command, and that will tell us what the nj's are for each group. How many groups are there? That's the number of nj's that we have, and what's the total length? That's the sum of the nj's. Okay. Now the combined ranking is easy because we can just rank the unlist of the y-list. Okay, so I didn't spell unlist correctly, and I didn't assign that to anything. So that gives us the ranks of everything. And then to sum the ranks from each group, it helps to have a map into the R vector. By that I mean to make a vector called G for groups, where I've got, just check out what this does. So sequence len m and j. So this makes a group variable that says the first so many, the nji. So what's nj? The first 10 of them are group 1, the next 9 of them are group 2, the next 26 of them are group 3, and the final 28 of them are group 4. Once I have that set up, I can do the group ranking as t-apply rg sum. There's many ways that you could do this, but I really like this. I think this is the tidiest shorthand to get the R bars for each group, because then I can just sum them up with sum rg squared divided by nj. So that gets us the final statistic. That should be called the final stat calculation. Okay, so that's our test statistic. Again, kind of a meaningless number without understanding the sampling distribution of this statistic with simulation. I'm going to always start with simulation, right? So we're going to do a big simulation. Let's do 100,000 to start with for I in 1 to n. Okay, so I'm just going to rs is sample 1 to n, n. Okay, just need a bunch of things to rank, and then since I've already set up this sum here, I can apply that on the virtual ranks that I just made, and these will be my virtual RGs, and then I can go sum them up. So look how I'm following the calculation of the statistic, but I'm using virtual ranks. That's always the trick, right? Follow the calculation of the statistic, but do it randomly, in this case with random permutations for the ranks. R2 bars, I think I already have this set up from earlier in the chapter, but it doesn't hurt. Rep NA N. Okay, so that should be RG. Where did I make a mistake? RGS should be, and I need to put an I here. That's an easy mistake that I keep making. Okay, so that is done. We can visualize histogram R2 bars. Okay, so there that is. And then AB line V equals R2 bar, all equals 2. I think we're going to reject this hypothesis. So that's going to be 2 times mean. Oh, it's not 2 times. It's a one-tailed test, right-tailed only, just like ANOVA with the F statistic is right-tailed only. So is this one. So we're just going to do mean of R2 bars greater than R2 bar. And that's our p-value. All right, how do we do it by, oh, you can't see it. I always make that mistake, but good thing I caught it this time. So now you can see the histogram that I made and the reason why I knew it was going to be reject, because the observed value of the statistic is way out into the tail and the p-value that we calculated is tiny. All right, so how do we do the Kruskal-Wallis test by math? Well, you're not going to like this. The KW test by math is SSP based. Okay, so that's subset sum problems. They're technically doable, but large values of the statistic, right? Our statistic, just going back here to put it back up, R2 bar, is 109,000. So we're going to have to figure out how all of these numbers, of which we have a total of n, how these 73 numbers add up to this really big R2 bar. There's a lot of ways to do that. So it's going to be a huge, leads to huge computation. Remember, solving SSP problems is NP hard, which is the hardest kind of problem to solve. It's fine if you have small numbers of numbers that you're trying to add up, but if you're going to do it for really big ones, it presents computational challenges. So what people do, here's the thing you're really going to not like, and there's way more about it in the book, but an inscrutable central limit theorem type argument provides the following approximation. So if you take this r bar squared value and subtract off its mean, I'm just going to tell you what that mean is, and there's a little bit more about that in the book, and then divide by its variance. So you're going to have 1 over n minus 1 times the sum. It's going to be a double sum, so j equals 1 up to m, and I equals 1 up to nj, rij squared. So I'm summing up the squares of all the ranks, and then centering it. And then putting that all together, you can show that this has a chi-squared distribution with m minus 1 degrees of freedom as n goes to infinity. So it's a central limit theorem. Central limit theorem is Gaussians, but we're working with squares here, and we know that squares of Gaussians are chi-squared. So that's what I mean by a central limit theorem-like approximation. So you can say the math way. So let's do this one step at a time. So the denominator is going to be the sum of our squared value. So that's how we get the double sum. We've already got all the ranks, right? So we just need to square them and add them up. And then take off this n times n plus 1 over 4 thing. And then we need to divide that whole expression by n minus 1. So that's the denominator. And then the numerator, or the whole chi-squared statistic, is going to be R2 bar, our statistic, minus n times n plus 1 over 4, and then divide by the denominator. So if I've done that right, the p-value is p-CHI-SQ, the statistic with m minus 1 degrees of freedom, lower equals false. Okay, so it's a tiny number. Remember, this is both of them are an approximation. We did a simulation-based approximation to get this number, and now we're doing a central limit theorem type approximation, and both are saying very low probabilities. Okay, so that is, oh, I see a mistake. And now I'm seeing why they don't agree more. I need squares here, so I've got a square if we look back at the formula, and also I need squares here. Let's go back through that. There we go, much closer. So we had what? We had 6 times 10 to the minus 5, and here we have 1 times 10 to the minus 4. So they agree to the 4th decimal place. That's the Kruskal-Wallis test.